In our previous videos, we have been using the new formulation of the second law of thermodynamics in terms of the enthalpy and entropy combine each other to give the change in Gibbs free energy. We have said that in some cases, when either this the enthalpy is negative and the entropy is negative, or the enthalpy is positive and the entropy is positive, in these cases the temperature will change the spontaneity. Notice that if the enthalpy is negative and the entropy is positive, it's always spontaneous, and the enthalpy is positive and the enthalpy is negative, it's never spontaneous. But in these two cases, one has to understand that there will be a temperature at which the process becomes from spontaneous to non-spontaneous, or from non-spontaneous to spontaneous. And this will depend on the temperature. A typical example is when you have a change of phase from solid to liquid to gas, etc. This is a typical example where there is a change of when there is a temperature at which the spontaneity changes. In this case, we're given not a phase change, but just a reaction of carbon with water giving carbon monoxide and hydrogen. Notice that from the entropic point of view, this is favorable. However, from the enthalpic point of view, this is not favorable. In other words, it's endothermic. It decreases the entropy of the surroundings by taking energy from the surroundings. So we are being asked at what temperature there will be a transition of spontaneity. Well, if you can plot it in the sense that reactants and products are plotted like here. At the beginning, at lower temperatures, notice that at low temperatures the entropic factor is less important, so what is important is the enthalpic, which makes it a delta G positive. Does that make sense? Well, the delta G is G of products minus reactants, always final minus initial, and in here the entropy of products is larger than the entropy. Gibbs free energy of the products is larger than the entropy of the reactants. This makes this positive. However, there's a temperature at which this is switched. How can we find that temperature? Well, at that point, the delta G will be 0. And this is a very typical problem when we just need to substitute. You will see several problems like these. At what temperature there will be this change of spontaneity? Well, if delta G is 0 at that point, and I know that 0 is delta H minus T delta S, one can just find out that I'm going to move delta H to the other side, minus T delta S, that is temperature, negative negative, positive, delta H divided by delta S. This formula will give us the change of spontaneity. Of course, if this process is the process of vaporization or freezing, this temperature would be the melting point or the boiling point, and so on. So careful in some problems when you're being asked what is the boiling point of this substance and you're given the enthalpy and the entropy. This is what you want to do. You want to find the temperature at which these two factors compensate each other so that you have a 0 in here. Okay, so let's do the math. The temperature is delta H, and a typical mistake is to find out that these two are different units, so I have to use always in the same units. So 1, 3, and I'm going to use in joules, divided by the entropy, 133.6. First of all, notice that the temperature is positive. If you get a negative temperature, you did something wrong, or probably you are applying this formula to one of these two cases. If you divide these two, what you get is this answer. At this temperature, this reaction up here will go from non-spontaneous to spontaneous. So in an industrial environment, you may want to understand at what temperature you may maximize the outcome of your reaction, and that's an important conclusion. a small detail here is that we have assumed that the enthalpy and the entropy do not change with temperature. Actually, we're given that these enthalpy and entropy are measured at 298 Kelvin. We assume that these values do not change with temperature, which at this level it's a good assumption. So notice that we obtained 983 Kelvin, very different from the temperature at which enthalpy and entropy had been measured. But if we assume that they're constant, this is a close enough solution.